All right, here's the cool stuff. This is where things start getting really crazy. I put the same pictures up on the board that we had before. So my parameterization is going to take things in the UV plane, which is just this simple grid, and it's going to spit me out some sort of magic carpet surface in a three-dimensional space. And the question that I'm asking myself is, I want to measure the surface area of this crazy three-dimensional carpet. So let's say that our U values are going from A to B, and our V values are going from C to D. So we're tracing out some rectangle here in the UV space. But when that translates over here, it's going to translate into being some subset of this crazy magic carpet space, right? Let's make it sort of the same size. And if I want to find the surface area of that crazy magic carpet space, it's not going to be exactly rectangular anymore. How do we measure it? Well, this is where we go back to what we were talking about before. So I'm going to get this vector right here is going to be given by T sub U times delta U, like this length right here. Let's take this little rectangular length. Maybe we shouldn't worry about too much of the specifics. It's going to have length delta U, like it's a tiny little rectangle. And this is going to have length delta V. It's going to be that length of that tiny little rectangle. And when I translate it over here, I end up with these two vectors. And I want to know, instead of approximating this by a rectangle, we're going to approximate with a parallelogram. So we're approximating the area of this tiny little parallelogram that was a rectangle over here, but when it gets mapped here, it becomes a parallelogram. And what is our surface area, or our area of this parallelogram? I'll give you 10 seconds to think about it, but it's given by a cross product, right? It's given by the cross product where the length of this side, maybe I should label my sides again, the length of this side is just T sub U times whatever the length delta U was, and the length of this side over here is going to be given by T sub V delta V, because these are the two tangent vectors, and together, if I want to know what the area of this parallelogram is going to be, it's just going to be the absolute value of T sub U delta U crossed with T sub V delta V. Because that's what the area of parallelograms are. It's the magnitude of a cross product. And so one thing is that these delta U's and delta V's, I can actually factor out that they're just scalars. And if I wanted to re-represent this, I could represent this as T sub U crossed with T sub V all times delta U delta V. But we have a name for this. T sub U crossed with T sub V, that's just our normal vector that we've defined previously. So this is going to be the magnitude of the normal vector times delta U delta V. But that's only the area for one of these little parallelograms, and we want to sum them up over all of the parallelograms, right? And so this is where we get up to our integration formula. That for our surface area, is going to be given by a double integral, and our U's are going to go from, what did we say, A to B, and our V's are going to go from C to D. And we're going to take this surface area, it's just the magnitude of T sub U crossed with T sub V, because that's the area of one of these rectangles, du dv. And if I wanted to shorten this formula a little bit, I don't have to write T sub U crossed with T sub V every time. Instead, I could just write this as the magnitude of V, or of n, where n is our normal vector, and maybe in the back of my head I'm still thinking that that's T sub U crossed with T sub V, du dv. And that's the way that I can find the surface area of a parameterized surface. I'm going to make it one step trickier. And the one step trickier is let's say that instead of finding just the surface area, so this is just the surface area equation, let's say instead that everywhere along this magic carpet there's some particular density. So let's say that I'm given a density function, and instead of finding the surface area, I want to find the mass of the carpet. So let me write down those pieces. The first piece is the fact that I want to find, so we're given the fact that, I'll erase this too because we don't need this picture anymore. So let's say that we're given that f of x, y, z is the density function. What does that mean? That means that at any point in space out here on our magic carpet, we're going to get a particular output that tells you what the density is right at that point. And I want to know, I want to sum up all of those density values over the entire carpet, because that's going to give me the mass of the carpet. So I'm trying to find the mass of the carpet. And so the mass in this case is going to be the density at each of these points all added up over the entire area. And by added up, I mean we're going to have to use a double integral. And the conclusion, maybe I'll write the conclusion and then I'll explain why the conclusion is really intuitive. The conclusion is that it's also going to be a double integral as u goes from a to b and as b goes from c to d. And I'm going to take my density function and I'm going to plug in whatever my function for my magic carpet is. This is my parameterization of my magic carpet, because I want to know what is the density at each of these places in my magic carpet. But then I also have to take into account how big the magic carpet is. So the area of that magic carpet is given by the magnitude of the normal vector du dv. So this is what we call a surface integral. And what is the surface integral calculating? It's calculating the mass of the carpet where I have a density function given by this function f. So this function f is the density function. I'm plugging in where is my carpet. This is the parameterization of my carpet. And then this term is telling me the area of the carpet, essentially. That this is going to be the area for each of these tiny little parallelograms. And so each piece right here is telling me the density at that tiny little parallelogram times the area of that parallelogram. So this is a tiny chunk of mass. And then I want to add up all of those mass chunks over the entire carpet. And that will give me the total mass, which is the surface integral.